The Dark Matter Particle Explorer, or DAMPE, has been collecting high-energy cosmic ray data since 2015, boasting good statistics, energy resolution, and particle identification capabilities. This research presents the latest measurements of the proton plus helium energy spectrum, spanning 46 GeV to 464 TeV. The spectrum exhibits a spectral hardening at 600 GeV and a softening at 29 TeV, with a statistical significance of 6.6 sigma. Notably, the detector's features and analysis approach enabled the extension of the spectral measurement to the sub-PeV region, suggesting a new spectral hardening at approximately 150 TeV, albeit with limited statistical significance due to the low event count. These findings are pivotal for understanding cosmic ray acceleration and propagation mechanisms, as they deviate from the expected single power law energy spectrum predicted by shock acceleration mechanisms. The observed spectral hardening and softening imply a complex scenario, challenging the traditional shock acceleration theory. The results provide valuable insights into the underlying physics of cosmic ray acceleration and propagation, highlighting the need for more sophisticated models that can accurately describe these phenomena. The Dark Matter Particle Explorer, or DAMPE, is a space-based detector that has been operational since December 2015, observing cosmic radiation up to 10 TeV for photons and E+E+ pairs, and hundreds of TeV for protons and ions, while searching for indirect signatures of dark matter. The instrument consists of 4 subdetectors: a plastic scintillator detector, a silicon tungsten tracker converter, a bismuth germanium oxide imaging calorimeter, and a neutron detector. This study utilizes a 6-year dataset collected between January 2016 and December 2021, applying an event preselection followed by a selection of protons and helium particles to both Monte Carlo and flight data. After accounting for instrumental dead time, on-orbit calibration time, a giant solar flare period, and South Atlantic anomaly passage time, a total live time of approximately 1.45 times 10 to the 8 seconds remains, corresponding to 76% of the total operation time. The preselection criteria include the activation of the high-energy trigger, an energy deposition higher than 20 GeV in the calorimeter, and energy deposition in any single layer of the BGO calorimeter lower than 35% of the total energy. The analysis employs Monte Carlo simulations with the GEANT4 version 4.10.5 toolkit and the FTFP_BERT physics list for protons and helium nuclei. Simulated events are initially generated with an isotropic spectrum following an E1 dependence and then reweighted during the analysis according to an E2.6 power law. Additional MC data are produced using alternative hadronic interaction models, specifically Fluke 2011.2X and DPMJET3 model for helium nuclei, and GEANT4QGSP_BERT for protons. The spectrum is computed anew using these MC samples, with the difference between the two spectra providing an estimate for the systematic uncertainty from the hadronic interaction model. The DAMPE detector employs a set of selection criteria for identifying protons and helium nuclei, including lateral shower containment, track selection, and charge selection. Lateral shower containment is achieved by requiring the shower axis to be within a central region covering 93% of the calorimeter width and rejecting events with maximum energy deposition at the lateral edges. Track selection combines STK information with measurements from other subdetectors, ensuring that the STK track matches the shower axis in the BGO calorimeter and is consistent with the signal in the PSD. Charge selection uses the energy deposited in the PSD, corrected for light attenuation, detector alignment, and incident angle, to identify protons and helium nuclei. A Landau function convolved with a Gaussian, Land-Gauss, is used to fit the PSD global energy distribution, providing the most probable value, MPV, and width value, sigma, of the function. The MPV and sigma values are dependent on the total energy deposited in the calorimeter and are modeled using a fourth-order polynomial function of the logarithm of the energy. The charge selection conditions are optimized to maximize statistics while maintaining a low background level. The effective acceptance of the DAMPE detector is evaluated using MC simulations and is found to be independent of the spectral shape or p-He mixture assumed in the simulation. Background estimation shows that protons constitute a background for helium, and vice versa, with electrons, positrons and lithium nuclei being the remaining background. The contamination from electrons is estimated to be around 0.5% at 40 GeV of energy deposited in the BGO calorimeter, decreasing with increasing energy. Lithium background is estimated using a template fit of the energy released in the PSD based on MC simulations, with a contamination of less than 0.3% up to 10 TeV and approximately 1.6% for energies higher than 10 TeV. The energy measurement and unfolding procedure are also discussed, noting that the energy of hadronic showers cannot be completely contained in the calorimeter. The Dark Matter Particle Explorer (DAMPE) data is utilized to analyze p+He measurements, with the particle shower detector (PSD) global energy distributions presented for events with deposited energy in the BGO calorimeter within specific ranges. These distributions are compared to Monte Carlo (MC) simulations of proton plus helium interactions, highlighting the charge selection ranges for p+He. The effective acceptance of the p+He analysis is calculated using MC samples, as shown in Figure 2, which reveals a significant decrease in acceptance at higher energies. A Bayesian unfolding procedure is employed to obtain the actual number of events in each true energy bin, utilizing the detector response estimated from MC simulations. This process accounts for the detector's response to both protons and helium nuclei after applying the selection cuts. The unfolded p+He flux is calculated and presented in Figure 3, covering an energy range of 46 GeV to 464 TeV. The results are compared with other direct and indirect measurements, with statistical and systematic uncertainties provided. The data is also reported in Table S1 of the supplemental material. Statistical uncertainties arise from Poissonian fluctuations in the detected events and the MC sample. To translate these uncertainties into the incident energy bins, a batch of toy MC samples is generated. The analysis has limitations and assumptions, which are discussed, along with potential future work. The paper presents a detailed analysis of the cosmic ray spectrum measured by the Dark Matter Particle Explorer (DAMPE) detector. The experiment has provided precise measurements of the cosmic ray spectrum in the energy range from 46 GeV to 464 TeV, collected between December 2015 and December 2017. These results are compared with other direct and indirect measurements from various experiments such as ATIC02, Nucleon, CREAM, Argo YBJ plus WFCT, HAWC, Cascade, and ESTOP plus Macro. The proton and helium spectrum was fitted using a smoothly broken power law (SBPL) function, revealing a spectral hardening around 600 GeV, followed by a softening at 28.8 plus or minus 4.5 TeV with a significance of 6.6 sigma. This hardening feature is consistent with previous results obtained by other experiments and earlier findings from DAMPE on proton and helium spectra. Moreover, the analysis confirms a softening feature in both the proton and helium spectra, as observed in previous studies. The systematic uncertainty band is derived from several contributions, including the hadronic interaction model used for the Monte Carlo simulation, the event selection procedure, and the assumed proton and helium mixture in the simulation. The main contribution to the systematic uncertainty comes from the hadronic interaction model, with an uncertainty of up to 15% for energy larger than 100 TeV. The spectral fit parameters obtained with the three analyses are reported in Table I, which suggests rigidity-dependent features, although a mass dependence cannot be ruled out. In conclusion, the paper provides a detailed analysis of the proton and helium spectrum measured by the DAMPE detector, contributing to the understanding of cosmic ray spectra and their implications for particle physics and astrophysics. The results are in agreement with previous measurements and provide new insights into high-energy cosmic ray physics. The p+He spectrum, measured over an extended energy range from 46 GeV to 0.46 PeV using 72 months of data from the DAMPE satellite, confirms the softening feature observed in individual proton and helium fluxes with an unprecedented significance of 6.6 sigma. This confirmation provides strong evidence for a change in the spectral index of cosmic ray particles, suggesting a complex acceleration and propagation history. Notably, the extension of the spectrum to higher energies reveals a new spectral hardening at around 150 TeV, establishing a crucial connection between direct and indirect cosmic ray measurements. This novel finding has significant implications for our understanding of cosmic ray sources, acceleration mechanisms, and propagation processes. The analysis leverages the high-precision measurements provided by the DAMPE satellite, which enables the characterization of the p+He spectrum with unprecedented accuracy. The results presented here demonstrate the power of space-based experiments in advancing our knowledge of cosmic ray physics. The research is supported by a range of funding agencies, including the Chinese Academy of Sciences, the National Key Research and Development Program of China, and the European Research Council, among others. These funding agencies have enabled the pursuit of cutting-edge research in cosmic ray physics, driving progress in our understanding of the universe. Efficiency validations for the DAMPE detector are presented, focusing on the high-energy trigger, het, and track efficiencies. The het efficiency is calculated using the unbiased trigger, UNBT, sample, which has a prescale factor of 1/512 when the satellite operates within the geographical latitude range, 20 degrees, 20 degrees. This efficiency is defined as the ratio of events that pass both the het and UNBT triggers, given by equation 4. Figure S2 illustrates the het efficiency as a function of the deposited energy in the BGO for Monte Carlo, MC, simulations and flight data, with a ratio of data to MC shown in the bottom panel. Track efficiencies are evaluated using the silicon tracker, STK, and BGO detectors. The STK track efficiency is calculated by selecting a sample of p+He based on the BGO tracks and PSD charge, and considering only the events that pass the STK track selection cuts. This efficiency is given by equation 5, where NBGO, PSD is the number of events selected with the BGO track that match the PSD charge, and NSTK, BGO, PSD is the number of events that pass the STK track selection cuts. Figure S3 illustrates the track selection efficiency as a function of the deposited energy for MC simulations and flight data, with a ratio of data to MC shown in the bottom panel. Charge selection efficiencies are calculated individually for each PSD layer, using measurements from the first cluster point of the STK track. The efficiency of the first PSD layer is determined by the ratio between events selected using the charge of both PSD layers and the first cluster point of the STK track, and events selected using only the second PSD layer and the first cluster of STK track, given by equation 6. The charge selection efficiencies for the first and second layers of the PSD are displayed in the top panels of figure S4. Comparing Monte Carlo simulations of protons and helium with flight data as a function of deposited energy. The bottom panels show the ratio of the efficiencies between the simulations and flight data, with the red dashed line indicating the variation within the uncertainties. Background contamination in the p+He spectrum is estimated to be low, primarily consisting of electrons, positrons, and lithium. Electron contamination is calculated by discriminating the morphology of proton-electron showers, as described in reference 38. Lithium background is estimated using a template fit of the energy released in the PSD, based on Monte Carlo simulations of protons, helium, and lithium. Figure S5 illustrates the estimated electron and lithium backgrounds, which are smaller than 0.4% up to 10 TeV and approximately 1.6% for energies larger than 10 TeV. The possibility of proton and helium interactions outside the considered fiducial volume but producing events that can survive the p+He analysis cuts has been considered. Dedicated simulations show that this effect can be neglected, being less than 1% at the highest energies and even smaller at lower energies. The unfolding procedure used to obtain the primary spectrum is described in the main text, where the number of events in the ith bin of true energy, N-AT, is derived from the formula 2, using the response matrix P-AT, EJO, derived from Monte Carlo simulations. The latter is shown in figure S6, where the color scale represents the conditional probability that the p+He candidates with observed energy AO are originated from true energy AT. This supplementary material page presents the response matrix derived from Monte Carlo simulations of protons and helium, following the application of selection cuts. The matrix represents the probability that an event in a bin of incident energy migrates to different bins of energy deposited in the BGO calorimeter. A table is provided, which elaborates on the p+He flux as depicted in Figure 3 of the main text. The page highlights the statistical and systematic uncertainties for the p+He spectrum, as shown in Figure S7. These uncertainties include errors related to the head trigger, charge selection, track selection, Phi mix, hadronic model, smearing correction, and BGO saturation correction. The total systematic uncertainties are also provided. The p+He spectrum from this work is compared with the DAMPE proton and helium individual spectra in Figure S8. This comparison shows good internal consistency between the datasets. The figure also includes the sum of the interpolated proton and helium individual spectra, along with their respective systematic uncertainties. A softening feature observed in the proton plus helium spectrum can be described by a smoothly broken power law model. To account for systematic uncertainties, a set of independent nuisance parameters are used and multiplied to the input model. A chi-squared function is defined to evaluate the fit quality, considering both statistical and systematic errors. The table on page 10 presents the p+He flux, along with its statistical error and systematic uncertainties from the analysis and hadronic interaction models. The data is organized into energy bins, providing median energy, E, low and high bin edges, E low and E high, and the corresponding flux, phi, in each bin. The model predicted flux in each energy bin is denoted as phi, A, and S, A, W, represents a piecewise function defined by its value W in the corresponding energy range covered by the JTH nuisance parameter. C, J is the covariance matrix of the fluxes obtained from TOI-MC simulations when estimating statistical uncertainties, and sigma SYS. J represents the relative systematic uncertainty of the data in such an energy range. The fit is performed in the energy range from 7 to 130 TeV, using two nuisance parameters. To account for the uncertainties on the fit parameters resulting from the selected hadronic model, the same fit is performed on the spectrum computed with MC samples simulated using the Fluka DPMJET3 and GEANT4QGSP_BERT models. The difference between the two fits is taken as a second uncertainty on the parameters. The results of the fit are phi 0 equals 1.35 plus or minus 0.09 times 10 carat 4 GeV carat 1 M carat 2 S carat 1 SR carat 1 gamma equals 2.512 plus 0.021 plus 0.010 0.0240 0.00 increment gamma equals 0.427 plus 0.066 plus 0.066 0.057 0.00 EB equals 28.8 plus 6.2 plus 2.94.40.0 TeV, and chi2, DOF equals 0.9, The parameter S was fixed to 5, which is consistent with the DAMPE proton and helium fit of the softening, 11, 19. To estimate the significance of the softening, the same energy region has been fitted with a single power law function, giving a result of chi2, DOF equals 48.14, which translates to a significance of 6.6 sigma. The SBPL fit of the softening is shown in Figure S9. In Figure S9, the p+He spectrum, in red, is fitted with a SBPL function, in black. Statistical uncertainties are represented by error bars, and the shaded bands represent the systematic uncertainties on the analysis, inner band, and total, outer band. The research examines the energy-dependent variation of the spectral index for DAMPE p+He data, employing a sliding window technique to fit the spectrum in plus or minus 2 bin intervals. The results are presented in Figure S10, where data points represent the gamma value with statistical uncertainty, and blue and light blue bands denote the quadratic sum of statistical and systematic uncertainties on the analysis and hadronic model, respectively. A spectral fit with a broken power law was performed above 30 TeV, disfavoring a single power law hypothesis at 1.5 sigma. This suggests that the spectral index undergoes a significant change at high energies, inconsistent with a single power law description. The study's findings imply that the underlying physical processes governing cosmic ray acceleration and propagation exhibit complex energy dependencies. The sliding window technique allows for a detailed examination of the spectral index variation with energy, providing insights into the underlying mechanisms driving the observed spectral features. By disentangling statistical and systematic uncertainties, the analysis provides a robust characterization of the spectral index, facilitating a deeper understanding of high-energy astrophysical phenomena. This study's results have important implications for the development of more accurate models of cosmic ray acceleration and propagation, highlighting the need for further research into the energy-dependent behavior of the spectral index. Unfortunately, there is no content provided to refine. Please provide the content you would like me to refine, and I will create a direct, concise, and technically accurate summary suitable for voiceover narration.